Forget everything you think you know about how the universe moves. We've been taught that everything eventually settles down, loses energy, and reaches a state of rest. But what if I told you there is a phase of matter that breaks the rules of time itself? Imagine a structure that repeats its pattern forever, not in space, but in time, without ever consuming a single drop of energy. It sounds like science fiction, but it's actually a reality that is currently breaking the brains of physicists everywhere. Welcome to Sci-Nova, where we dive deep into the weirdest corners of our reality. Today, we are talking about the discovery of time crystals. For decades, the laws of physics suggested that such a thing was impossible, a perpetual motion machine in disguise. But the universe loves to prove us wrong. We're going to explore how these strange structures work, why they shouldn't exist according to classical logic, and how they might eventually become the heartbeat of the next generation of supercomputers. And to understand a time crystal, we first have to understand what a regular crystal is. Think of a diamond or a snowflake. In a normal crystal, the atoms are arranged in a repeating pattern through space. If you move from one atom to the next, you see the same structure repeated over and over. This is called spatial symmetry. It's predictable, it's stable, and it's the foundation of much of our physical world. But time crystals take this concept and turn it on its head by moving the repetition from space to the dimension of time. In 2012, a theoretical physicist named Frank Wilczek proposed the existence of these strange entities. He wasn't looking for a way to build a perpetual motion machine, which is strictly forbidden by the laws of thermodynamics. Instead, he was exploring a concept called the spontaneous breaking of time translation symmetry. In simple terms, this means that while the laws of physics don't change from one moment to the next, the system itself chooses to repeat a pattern at specific intervals. It's like a clock that keeps ticking even though nothing is winding it up. Now, you might be wondering, if they don't use energy, are they breaking the second law of thermodynamics? The short answer is no. Time crystals are unique because they exist in non-equilibrium systems. In a normal system, if you keep adding energy, things eventually heat up and become chaotic. But a time crystal stays in a stable, repeating state even when it's being driven by an external force. It doesn't create energy out of nothing. It just manages the energy it receives in a way that allows it to maintain a rhythmic, structured dance through time. The theory remained a beautiful mathematical idea for a few years until the experimentalists stepped in. Since at least 2016, physicists have been successfully observing discrete time crystals in actual laboratories. This wasn't just a simulation on a computer. These were physical, observable phenomena. By using highly controlled environments like trapped ions or quantum simulators, scientists were able to witness the spontaneous breaking of that time translation symmetry in real time. It was the moment the impossible became observed. But here is where it gets even more relatable. You might think this is all happening in some far-off, high-budget facility, but the building blocks might be closer than you think. Researchers have actually used liquid crystals, the same kind of material used in your smartphone's LCD display, to create structures that mimic the behavior of time crystals. By manipulating these liquid molecules, scientists can create patterns that oscillate in time, providing a more accessible way to study these quantum wonders without needing a multi-billion-dollar particle accelerator. So why does this matter to you? Or why should we care about a bunch of atoms dancing in a lab? Because time crystals are a potential game changer for the future of computing. One of the biggest hurdles in quantum computing is decoherence, the tendency for quantum information to get lost or corrupted by the slightest bit of environmental noise. Because time crystals are inherently stable and resistant to certain types of disruption, they could potentially be used to create incredibly stable quantum memory. Imagine a world where quantum computers don't just crash because a stray photon hit them. If we can harness the stability of time crystals, we could store quantum states for much longer periods. This would allow us to perform much more complex calculations, solving problems in medicine, materials science, and cryptography that are currently impossible for even our most powerful supercomputers. We aren't just looking at a new phase of matter, we're looking at the foundation of a new era of technology. Let's take a moment to recap what we've learned. We've gone from the concept of spatial symmetry in diamonds to the mind-bending concept of time translation symmetry. We've seen how Frank Wilczek's theory moved from paper to the lab in 2016. We've learned that these aren't magic perpetual motion machines, but non-equilibrium systems that break the rules of how we thought matter behaves. And finally, we've seen how even the liquid crystals in your pocket might hold the key to this quantum revolution. The discovery of time crystals reminds us that our understanding of the universe is always a work in progress. Every time we think we've mapped out the boundaries of what is possible, nature presents us with something that defies our logic. It challenges us to rewrite our textbooks and rethink our fundamental assumptions about time and energy. It's a reminder that the most profound mysteries aren't always found in distant galaxies, but in the very structure of the matter right in front of us. As we continue to probe the quantum realm, who knows what else is waiting to be found? Maybe time crystals are just the tip of the iceberg. Maybe there are even stranger phases of matter that we haven't even dreamed of yet. The more we learn, the more we realize how much we have left to discover. And that is the most exciting part of science. The fact that the unknown is always larger than the known. If you found this journey through the quantum world fascinating, make sure to hit that subscribe button and join us here at sci-nova. We're constantly exploring the frontiers of physics, biology, and the cosmos to bring you the most incredible stories from the universe. Don't forget to ring the bell so you never miss an update on the mysteries of reality. Thanks for watching, and keep staying curious.